Hello and welcome to my presentation. My name is Christopher Clark, and today we will be discussing my results as a consultant for the Aging Wisely project by Dr. Ben Green, Katie Green, and Scott Fisher. So our motivation and background is simple. We would like to understand what are the psychological, psychoanalytical, and demographic factors that are most strongly associated with someone having aged wisely, with somebody who has lived a life that they accept and is ready to move on to whatever comes next. To do so, our two investigators, Dr. Ben Green and Scott Fisher, conducted 52 two-hour interviews with elderly individuals in Colorado and Massachusetts, ranging from age 68 to 95 years old. Some of these participants were known to the interviewers, and some were references, and still others were members of the Allied Jewish Home. During these two-hour interviews, about half the interview was spent allowing the participant to talk about themselves with a little guiding and a little prodding, and the other half was a more traditional question and answer session. Now, each investigator ranked each participant on 28 psychological and psychoanalytical factors. Also, several different demographic variables were recorded, and these will be discussed in the subsequent slides. Finally, an overall impression of aging, the global clinical impression, was recorded for each. And this global clinical impression is the score that we associate with aging wisely, the score that we're going to be interested in understanding and interested in modeling. Now that we have a good idea of our background, motivation, and overarching broad goal, we can break it down into several smaller questions that we will answer throughout this presentation. The first has to do with the interviewers themselves. Given that this was a multi-year project, we're interested in knowing whether or not, as the experience between the two grew, as the number of cases that they interviewed increased, did they converge on their thinking? Did they converge in their grading? The second has to do with the correlations and relationships between the factors and this global clinical impression and composite metafactor score, which will be discussed in subsequent slides. The general idea being that here soon we will actually break apart the factors into various groups. And we're interested to know, for example, is there one factor within that group that has a very strong correlation with all the rest, or is there one factor that perhaps is more important among that group than the rest, or are there interesting relationships between two different groups of factors, not necessarily looking at the global clinical impression and composite metafactor score. The third and most interesting question, the main goal of the project, is to figure out what are the factors that are most indicative of a high global clinical impression or composite metafactor score. Once we have a rough idea of what that is, we can then ask, does age affect any of this? Does age affect the relationship between the factors and these outcomes? And finally, we have several different demographic factors for each case. We're interested to know if, in particular, this residential status, or how one lives, if one owns a home or is living in assisted living or something like that, has a significant relationship with the factor competence, which is about how well somebody is able to get along in their life. So now let's dive into the actual variables themselves in a little more detail. So we have our demographic variables. These are things like age, gender, marital status, ethnicity, so on and so forth. And in particular, residential status and age are what we're going to be most interested in for this particular analysis. The 28 factors can be grouped into metafactors, which include things like gratitude or purpose and meaning, elder developmental task, controllable protective factors, other, so things like sense of humor and other factors that don't neatly fit into these other groups that the investigators still believed would end up being important. Interview presentation variables, like what was their mood, their candor, did they have narrative coherence when they were telling their story? And elder identity revision, another one that the investigators are quite interested in understanding. Elder identity revision and metafactors being the ones that we believe are going to be the most important and that we're most interested in seeing the effect. So these are things like elder identity revision are things like control and connection. And finally, we have this composite metafactor score, which we mentioned in the earlier slides, which is just a sum of the 5 original metafactors, and can also be thought of as a benchmark for aging wisely. So instead of just the global clinical impression, there's this other potential marker for having aged wisely, and we're interested in the relationships between all of them. So let's look at this graph here for a second. This is just case one, this first person. We can see there, these are the average rankings. So remember that both Dr. Ben Green and Scott Fisher gave their grades and then they were average. So sometimes they sit on a whole number, sometimes they sit on a half number. So for example, we see in the lower left, we have gratitude. This person, case one, was ranked an average of 5. Whereas, for example, keeper of meaning, this low point right here, a little more to the right, is a 3, and this openness was this very low point right here, scored a very low score of 2.5. So this is just a rough view of, for example, what case one, how they were graded, what they looked like after this project was said and done. So now let's talk a little bit more about our data, our measurement scales, and the potential linearity. So all of our factor data and the global clinical impression are rank or ordinal data. So the phrase that we use is Likert, and they're all on a scale from 1 to 5, except for one of them, which was on 1 to 7, and we then transformed to 1 to 5. The composite metafactor, as we said, is a composite score of all 5 metafactors, which means it runs from 5 to 25. We also transformed it on to a 1 to 5 scale. So one of the things that we want to see is if our data seems roughly linear against the outcomes that we're interested in, the global clinical impression and the composite metafactor score. And to do so, we can simply plot them. For example, we see here in this first plot, this gratitude versus global clinical impression. We have what appears to be a pretty strong linear relationship. And in the generativity versus the metafactor total, composite metafactor score, we have, again, what appears to be a significant linear relationship with an interesting bit of an outlier over here in this 4.5. So that is quite interesting and actually will come up. So this actually allows us to feel confident that we can use some of our modeling techniques that we're going to use. Question 1, did the interviewers become more consistent over time? So probably the easiest way to determine this is to take a simple plot of the difference between each interviewer's grade across all the cases for each factor. So for example, here we have our elder developmental tasks, a grouping of factors that has generativity, keeper of meaning, and ego integrity. And we can see on the x-axis, it runs from 0 to 51, which is just a quirk of the programming language we use. That means that it runs from the first case all the way to the 52nd case, so all 52 cases. And we simply chose to take Scott Fisher's grade for that specific case minus Dr. Ben Green's. There's no particular reason for this. We could flip it and this chart would look the same, just flip. And what we would like to see if we had consistent grading is a simple flat line, right? Because they would have the same grade. So if you take that grade and subtract itself, you would get 0. However, we actually find quite a bit of difference here. These spikes are differences. When we have a positive spike, that said that Scott Fisher's grade for that particular individual and for that factor was higher than Dr. Ben Green's, and vice versa when it's in the negative. In fact, we can see, for example, here in the 24, maybe case 23, 24, and then again at case 42, with ego integrity and generativity, we see a very large jump. So what we would like to see, assuming that the interviewers became more consistent over time, is a large number of spikes or these plateaus that you'll see among the first cases with a much lower frequency as the interviews go on, as the case number increases, and we actually don't see that This graph here is quite typical of the various grade differences that we do in fact find. The overall average discrepancy, so we find the discrepancy across all factors per case, and then we can find the average discrepancy of those numbers is negative 0.09. So on average, it's about 0. So this tells us that on average, roughly we have as much of a difference between in the direction of Dr. Ben Green and Scott Fisher. The standard deviation of the discrepancies is 0.26. So again, we take that number, those averages across all 52 cases, we find the standard deviation and we get 0.26. So roughly a quarter of a point or so standard deviation. Now, let's talk a little bit about correlations. So given that our data is Likert and ordinal, we need to use Spearman's rho. So the very first thing we do is we run a test between every single possible pair of factors, global clinical impression, and composite metafactor score. Now, given that this is 30, you would have 30 times 30, but of course we know that the correlation between a set of data and itself is just 1. So in fact, we can throw out 30 of those. So we have 870 different correlation tests, and in every single one, we find a p-value less than or equal to 0.05. Now, this allows us to say that there is very likely a real relationship, a real association, that the correlations are not statistical anomalies. And this is great because we can proceed feeling very confident that the correlation numbers, that this row that we get, does represent something actual, again, as opposed to a statistical anomaly. So in order to visualize our correlations, we use something called a heat map, where very bright colors mean a very strong correlation, and very dark colors mean a very low correlation. And it's important to keep in mind that this is relative. So for example, the lowest, what we're about to see with this heat map here, is that the lowest correlation is given a color black, but is actually 0.66, which is quite high. But before we talk about that, unfortunately, our heat map with all of the factors, global clinical impression and composite metafactor score, is simply too large to place here. So we'll just talk about the highlights. The big one being that the largest correlation between any of the factors or our two outcomes of interest is actually between ego integrity, which we remember is an elder developmental task, and global clinical impression. And in fact, we have rho equals 0.92. This is a very strong correlation. And we're actually going to see, as we move through our other models, that this relationship between ego integrity and global clinical impression continues to show itself. Now, between global clinical impression and composite metafactor score, remembering that we were thinking that the composite metafactor score might be another metric by which we could age how somebody has aged wisely, we find a correlation of 0.82. So again, quite high. Now, as a little example of what this would look like if one were to go in the code or go into the paper, here is a heat map of Spearman's rho, these correlation coefficients, just between the metafactors. So we have 5 metafactors, 5 by 5. This table is going to have 25 different values. And we see along the diagonal, that is where the row meets the column. So that is where one factor has found its partner, itself. And so, of course, those correlations are going to be 1. So we won't look at those. We'll look for other high correlations or low correlations. And in fact, we see this bright orange right here between resilience and purpose or meaning. We have a rho of 0.89. So again, a very, very strong correlation between these two metafactors. The lowest being this these black squares here between active habits and self-acceptance or self-esteem. But again, even though that's the lowest among them, 0.66 is still quite high. So thinking about whether or not all of these factors are necessary, this at least says that between resilience and purpose, and meaning you could probably get away with just doing one. You wouldn't really lose a whole lot by just choosing one. And in fact, given the very high correlation between all of them, it definitely seems as if maybe one could cut down this set of 5 into a smaller set. And in fact, we actually find that as we keep going, as we look at some of the other correlations, which we'll do in the next slide. So let's talk about some of the other correlations. As I mentioned, we have several different groups that we were interested in looking at. So looking at just the meta factors, we have resilience and purpose, as I mentioned, with a row of 0.89. Among the elder identity revision, we have consciousness and connection, have the highest of row equals 0.82. Among the elder developmental tasks, we have ego integrity and generativity with a row of 0.76. And between elder developmental tasks and elder identity revision together, looking at just the combinations of those, we have ego integrity and connection with a row of 0.82. Moving on to question 3, our most important question, we're now interested in building models that can tell us a little bit about the relationship beyond just correlation between the various factors and our outcomes. And we're going to build several different models. In particular, we're using multiple linear regressions. These are models that have the advantage of being very interpretable. It's very easy to read off the coefficients that they give and see immediately which factors are the most important and how much they contribute to the outcome in question. So we have here a list of all of our regressors or factors, and we're trying to fit a model that uses them to explain and predict the red underlined outcomes, which are either global clinical impression or the composite metafactor score. So let's talk a little bit how we build our regressions. So first and foremost, if we go back 1, we see that the first 2 are between all of the factors, so all 28 factors and global clinical impression. So we're trying to fit a model that has all the factors as regressors or independent variables. And what we're trying to get, what we're trying to make sense of and predict is going to be this global clinical impression. And the next one is the non-meta factors, of which there are 23. And composite metafactor score. Now, the problem is that if you then think about how many different models you can make with 28 or 23 factors or regressors, these are very large numbers. So we can't do what we would call an exhaustive search where we check every possible model. Instead, we're going to do a forward stepwise search by AIC. So very quickly, what this means is that we're going to fit a model with just every regressor, and we're going to pick the lowest AIC, and we're going to take that model and we're going to now begin fitting for all of the non-used regressors and see if we can find a model that's lower, and so on and so forth until we get to a model or a step where all of the models, after we add a new regressor, a new independent variable, a new factor, then we begin to see our AIC increase. Now, why in particular are we interested in AIC? So AIC is the Akaki Information Criterion, and it is a metric that combines the complexity with the explanatory power. So the general idea being is that we can keep adding regressors and we're going to get more explanatory power, but we may run into the issue of interpretability, especially with such high correlations. We might start getting really weird numbers. And we also just generally want to invoke the principle of parsimony to get the simplest models that are the most predictive. So the AIC is a good metric to do so. After we have a model, we're going to check a histogram and QQ plot, which we can see some examples in the paper, but this allows us to see if the model is actually well fit or if there's some outliers or if perhaps this whole enterprise isn't going to work. If we find some outliers, we're going to remove it. We're also going to look for p-values associated with each of the coefficients, and this tells us if the model doesn't believe that the coefficient is statistically significant. It may aid in the prediction, it may explain some of the variance, but it might be the case that for whatever reason it's just not statistically significant. So when we do that, we can actually do this really neat plot here where we plot the AIC of our models as we move through the steps. And what we expect to find is that we'll get to a point to where the amount of decrease of AIC begins to drop off relative to the number of regressors that we continue adding. And the way to interpret this is simply that we're getting diminishing returns, right? That we're very, very, very slightly increasing the power of our model, but we're dramatically increasing the complexity. And this is what's happening, is that these p-values are telling us that these regressors, these factors may not be important, they may not be statistically significant, but we are still getting some kind of explanatory power, and we don't want that. That's going to give us issues with interpretability and things like that. So in this little graph right here, we can see starting at step 0, which is the first model, we see that right around step 3, it really starts to drop off. So this means that with just 3 or 4 factors, we get a good model that, though it is possible to have a lower AIC, we end up when you actually fit this model, you actually end up with all of the regressors being statistically significant with a very high R-squared score, which is a measure of fit, or a measure of how well the model is explaining the variance. So it's a bit of a trade-off. We get a little bit less, very so slightly less explanatory power, but we get a model that we feel quite confident that all of our regressors are significant, and that is far more interpretable, as we don't have these issues with the regressors interacting with each other. However, for the next several sets, going back to, so these next 5, these are much smaller sets of regressors. So we can actually do an exhaustive search. We can check every single possible model. And the general idea is basically saying we run through the models, pick the lowest AIC, check and see if we run into an issue where we have statistically insignificant regressors. We can check an AIC versus stepwise step to see whenever we start getting those diminishing returns, and then just cut off our models at that number of regressors. So, for example, 2 of the most important ones, for the all factors versus global clinical impression, we found, in order of highest coefficient, ego integrity, gratitude, and connection. Now, remembering that in our correlation, our Spearman's row correlations, we had ego integrity having the highest correlation with global clinical impression, this shouldn't be a surprise, right? We should definitely expect that ego integrity will show up, because our correlation is definitely saying that there's something going on there, and now our multiple linear regression models are also picking out this factor as being quite important. We also find, remember, gratitude was a metafactor, so that's quite interesting that we find a metafactor. We expected those to be important, and we in fact find one. And we also find connection, which is an elder identity revision. So this is quite interesting. For the non-metafactors versus composite metafactor score, we end up with mood, generativity, narrative coherence, and tragic optimism. And then now, just looking at the metafactors versus global clinical impression, we have gratitude, self-acceptance, self-esteem, and resilience. Now, again, we expect this because gratitude, which was a metafactor, showed up in the regression with all of the factors. So now, just focusing on the metafactors, it shouldn't be a surprise that this shows up. So this right here, again, we have all of these other regressions that we won't go into. They're in the paper, but these are, in my opinion, the most important, and my understanding are the ones that are the most interesting for the project. So now that we're done with our regressions, let's begin to answer the question of whether or not age has an impact on anything we've done thus far. So in order to do that, we're going to take each of the final models in our original regressions, and we're going to add age as a main effect, scaled from 1 to 5, of course, and age times factor for every factor, again, scaled 1 to 5 as an interaction term. And then we're going to rerun our selection, our model selection, in the exact same way that we did. And it turns out that we find that age is only significant in the regression with the elder developmental task factors versus composite metafactor score. So we can see here these 2 printouts, what our original model looked like versus our model with age. So in our first model, the one to the left, we see ego integrity and generativity being the most important, and being the regressors that were left over after all of our simplification processes. And this has an R² score, a score of how well the model is fit, of 0.979. So this is quite a good model. However, when we add age and then age times ego integrity and age times generativity, so we now have 5 factors, and we run everything as before, we end up now with 3 factors that are left: ego integrity, generativity, and age. And in fact, what we see is the coefficient for ego integrity and generativity has dropped a little bit, or have dropped a little bit. And we now have this new factor of age with a much smaller coefficient, which we interpret as saying that age definitely contributes less to the composite metafactor score, but it does contribute in a statistically significant way. We see this p greater than t column over here, that we have a p-value of 0.007. That's quite small, and therefore we believe this is quite statistically significant. And now comparing the fit of the model with these 3 regressors versus the fit of the model with just the 2, we actually have a very slight increase in an R² score that now sits at 0.982. So we can say that at least for this particular set of factors, the elder developmental tasks with the outcome of composite metafactor score, that age does contribute, and age is statistically significant. So for the next algorithm that we're going to use to see how we can determine the relationship between these various factors and our outcomes of interest are clustering algorithms. So clustering algorithms do pretty much what they sound like. They attempt to find clusters or groups in the data. The idea being that if we have a rough idea how they can be grouped or clustered, we can figure out how the data points in the individual clusters relate to each other. So the simplest way to figure out if this would be a good idea is to simply plot the data and see if we can actually see some clusterings. The problem is that with, for example, our 28 factors, we can't do that. So what we're going to do is run something called principal component analysis, which is going to take our original data set and return the same number of principal components as dimensions or as factors in our original data set, but these principal components are going to be ordered in terms of how much of the variance, or informally the information they contain about the original data set. And this way we can hopefully plot just a few of the first components in 2 and 3 dimensions and get a rough idea of what our original data set looks like. So for example, here we see that the first component, principal component, on the data set with 28 factors contains roughly, or accounts for roughly 65% of the variance, and the second about 70, and the third about 75. So we can actually plot these 2 and 3 principal components and visualize them. And though we understand that we're going to miss some of the variance, we should get a pretty good idea of what the original data set looks like. So let's do that. So when we plot the first 2 and first 3 principal components of the data set with 28 factors, we see a little bit of clustering in both of them, but a little bit of scattering. So we are going to go ahead and run our algorithms, our clustering algorithm, but we understand that we don't want to put as much weight in it as, for example, our multiple linear regressions. However, some of our data sets, for example, the elder developmental tasks, only has 3 factors. So for this one, we can actually just visualize it outright. So in this case, we didn't need to run principal component analysis. We could just visualize it. And again, we see that they're kind of grouped together, maybe. We don't see quite as many clusters, but there's still a little bit of spread. So again, we're going to run our clustering and see what happens, but we also don't want to put too much weight into it. So let's just review the results for the very first clustering on the data set with 28 factors. So what we're going to do is we're going to print out the first couple of groupings. So what a case was assigned to, what group it was assigned to, and then the global clinical impression to see if there appears to be any overlap, or if it appears that the clusterings have encountered something or found something interesting. So for example, we see here in our first couple of groupings and global clinical impression scores that it does appear, for example, we have a 3 that got grouped in 1, a 2 that got grouped in 1, a 5 and a 4 that got grouped in 0. And in fact, in our script, we run through and show this, that it actually does a pretty good job, about 92% clustering low and high GCI together. So that's pretty interesting. And we can now check and see what are the factors that this algorithm considers the most important for each group. And the way we do that is by simply figuring out how far along the axis of that factor the algorithm placed the center of the group. The idea being that the center of each group is what the algorithm has determined is the canonical member, the exemplary member of that group. So if we look at the exemplary member of the high global clinical impression group, we find that the three most important contributors to that exemplary member are engagement, cognitive, and gratitude in that order. So right off the bat, we see something kind of interesting. It's a bit different from what our regressions gave us, but we do still see gratitude. And in fact, as we run all of these, what we're going to find that it turns out to be quite interesting is that when the number of factors is quite large, like for example, in 28 and 23, we find quite a bit of disagreement between the clustering algorithms and the regression algorithms. But when the number of factors is quite small, we get very good agreement, oftentimes the exact same factors and in the exact same order of importance. Now, moving on to our final question, we can ask, what is the relationship between the demographic variable, residential status, and the elder identity revision factor, competence? So to do so, we're going to divide all of our 52 cases into two groups based on their residential status. We're going to put everyone with H into one group and everyone with anything other than H into another group. And this way we get a more even division between the two groups, and both groups will have quite a few members. So this helps us out. Now we can just find the average competency score of the two groups. For residential status, we have an average competency score of 4.1, and for anything other than H, we have 2.94. Now, though that seems like a large difference, we're going to go ahead and run another statistical test, the Fisher's exact test, to determine whether or not there's evidence to believe or whether or not we're confident that this relationship is genuine. We find a very low p-value. So we can state that with very high confidence that there is a genuine dependence between residential status and competence, and further that a residential status of H is strongly associated with a larger competence score. And this is what we expected, and so it's quite nice that we ended up showing what we thought was going to happen. So we can summarize quickly the answer to the question of how does one age wisely? It appears, based on our models that we feel the most confident in, our multiple linear regressions, that ego integrity, gratitude, and connection are the most important for a global clinical impression, which we are taking as our canonical measurement of aging wisely. Further, because of the very high between ego integrity and global clinical impression, we can go one step further and say that ego integrity should be the most important. And this is quite interesting because we in fact have a meta factor in gratitude, we have a elder developmental task in ego integrity, and we have an elder identity revision in connection. So these three groups of factors that we expected to be important ultimately did end up being important. So though these results are quite interesting, how could we improve upon our study? How could we improve upon these results? Probably the most obvious is simply getting more participants, and further getting more participants of a more varied geography or varied location. It would also be interesting to see what would happen if we got, for example, more graders, so that perhaps we could bring that variance between the gradings down a little bit. Perhaps having 3 or 4 graders would lead to a lower variance in the grading than just having 2, where on occasion they could disagree by up to 2 points. And finally, in order to sidestep this problem of qualitative data, qualitative judgments, perhaps introducing some more quantitative factors, some things that are not really up for interpretation, some things that can be measured in a more precise way. If we were to implement all these, it is my opinion that we would be able to generalize our results a little bit further beyond and feel a little bit more confident with those generalizations than we can right now.